Good evening, sir. You can start, sir.
Ma'am, you have not made me a host.
I made you a host, sir.
No. Check, ma'am. You have made Dhanushri as a host, not me.
Good evening, sir.
Yeah, good evening. How many of you are there? Ma'am?
Yes, sir.
Oh, ma'am. You didn't make me a host yet.
Sir, you can start, sir.
Ma'am, you have not made me a host, ma'am.
I made you a host, sir.
No. I'm not able to share the screen. Host disabled participant screening, it says. Hello?
Sir, just a minute, sir.
Yeah. Okay, now I'm a host. All right, we'll continue. Yesterday we learned with the Faraday's laws. Yesterday we finished, not yesterday, last week, 2 days before, we finished Faraday's laws. Both first and second law we did with the theory part and the numericals. And we also started with the metallic and the electrolytic conductors. We also learned the difference between metallic and electrolytic conductors. Metallic conductors, it is due to the flow of electrons. We learned. Metallic conductors means metals which can conduct electricity like copper, aluminium, gold, silver. All these are metallic conductors. Now, electrolytic conduction means electrolytes in solution state. Conductivity in solution state is called as electrolytic conductor. In case of metals, the current is carried due to the flow of electrons. In case of an electrolyte, the current is due to the flow of ions. In case of a metallic conductor, no decomposition takes place. But in case of an electrolytic conductor, the electrolyte undergoes decomposition. Both physical change as well as chemical change takes place. In case of metallic conductor, there is no involvement of transfer of matter. But in electrolytic conductor, it involves the transfer of matter in the form of ions. Ions move towards the respective electrodes. That is what it means. They involve transfer of matter in the form of ions. Now, metallic conductivity decreases with increase in temperature, because as we increase the temperature, what happens is the resistance increases. Since resistance increases, conductivity decreases. Now, we should know that conductance is the reciprocal of resistance. Since resistance increases on increasing the temperature, conductivity of the metallic conductor decreases. But in case of an electrolyte, conductivity increases with increase in temperature, because on increasing the temperature, these ions will start moving faster towards the respective electrodes. So since ions can move, ions gain more of kinetic energy and it will start moving faster. Therefore, conductivity will increase in case of electrolytic conduction on increasing the temperature. Now, electrolytic conduction. When a voltage is applied to the electrodes dipped into an electrolytic solution, ions of the electrolyte move and therefore electric current flows through the electrolytic solution. The power of electrolytes to conduct electric current is termed as conductance or conductivity. Now, the simple experiment, we have done this. Now, I take a container. In this container, we have an electrode. anode and cathode, connected to a power supply. And in this, we have an electrolyte. Now, an example for an electrolyte, I take sodium chloride. On passing current, what happens is sodium ion move towards the negative electrode and chloride ion move towards the positive electrode. These movement of ions will carry what current, and it's termed as conductance or conductivity. Due to the movement of ions, electricity will be conducted, and that is termed as conductance or conductivity. Now, this is based on Ohm's law. What is this Ohm's law? In physics, you would have learned Ohm's law. This states that current flowing through a conductor is directly proportional to the potential difference across it. So I is directly proportional to V. This is Ohm's law. Current flowing through a conductor is directly proportional to potential difference. Potential difference is otherwise called as what? Voltage across it. Where I is the current in amperes and V is the potential difference in volts, or we can write, if you remove the proportionality sign, we give a proportionality constant. So I will be equal to V by R, or V is equal to IR. This is the mathematical representation of Ohm's law. All right. Now, where R is the constant of proportionality and is known as resistance, R is known as resistance of the conductor. It is expressed in ohms and it's represented as ohm. This is an ohm. This is the representation. This is the representation ohm. So the unit for resistance is ohms. The unit for resistance is ohms. It is represented by the formula or representation omega like this. The above equation is known as Ohm's law. Ohm's law may be stated as the strength of current flowing through the conductor is directly proportional to the potential difference across the conductor and inversely proportional to the resistance of the conductor. I is equal to V by R. So I is directly proportional to voltage or potential difference, and I is inversely proportional to resistance. So this is the mathematical representation of Ohm's law, or we can write it as V is equal to IR. Followed with this?
Yes, sir.
Yeah, the next one is the resistance. It is the measure of obstruction to the flow of current. So the force which opposes the flow of current is called as resistance. It's called as, it's a measure, it measures the obstruction of flow of current. The resistance of any conductor is directly proportional to length and inversely proportional to area. So we should write it like it's not equal to sign, it is proportionality sign. Resistance is directly proportional to length and inversely proportional to area. That means longer, more the length, resistance will be what? More. And resistance is inversely proportional to area. So if you remove the proportionality sign, we give a proportionality constant. This proportionality constant is called as rho, RHO. It looks like P, it is not P. It is a rho symbol. It is the constant of proportionality and it is called as specific resistance or resistivity. It is called as specific resistance or resistivity. The resistance depends upon the nature of the material. The resistance depends upon the nature of the material. Now, what is resistance? It measures the obstruction to flow the current or flow of current. The resistance of any conductor is directly proportional to the length and inversely proportional to the area of cross section. Length is represented as L and area is represented as A. So R is proportional to L by A, or R is equal to rho into L by A. Rho is called as proportionality constant and it is named as specific resistance or resistivity. The unit for resistance is ohm. In terms of SI units is equal to kg meter square per centimeter cube A square. So don't worry about this. Don't worry about this. It is in terms of what? Ohms. The resistance, the unit for resistance is what? Ohms. The next is resistivity or specific resistance. Now, how do we define resistance or resistivity or specific resistance? We know that resistance R is equal to rho into L by A. If L is 1 centimeter, if the length of the conductor is 1 centimeter and area is 1 centimeter square, then what happens? Now we know that R is equal to rho into L by A. They say L is equal to 1 centimeter and area A is equal to 1 centimeter square. So what happens? R is equal to rho into 1 by 1. So R becomes what? Rho. So thus resistivity is defined as resistance of the conductor of what 1 centimeter length and having area of cross section 1 centimeter square. So resistivity is defined as resistance of the conductor of 1 centimeter length and having the area of cross section 1 centimeter square. Did you understand what is resistivity? Do you understand what is resistivity? Resistivity or specific resistance, did you understand? Resistance
Yes,
or specific resistance becomes equal when length is 1 centimeter and area of cross section is 1 centimeter square. Next. Units for resistivity is ohm centimeter. The unit for resistivity is ohm centimeter. Its SI units are ohm meter, but quite often ohm centimeter is also used. So the SI unit for resistivity is ohm meter. Quite often it is ohm centimeter is also used. Now coming to the important topic, we'll have to work out numericals based on conductance. We'll learn conductance. It is the measure of ease with which current flows through the conductor. It is an additive property. It is expressed as G. Conductance can be represented as C or it can be represented as G. Conductance is simply defined as the reciprocal of resistance. The reciprocal of resistance is called as conductance. See, it is written here also. It is the reciprocal of resistance. That is, G is equal to 1 by R, or conductance C. We can represent it as C also. C is equal to 1 by R. The units of conductance are the reciprocal of ohm. That is ohm inverse, or we write it as mho. Ohm is also abbreviated as O, so that ohm inverse is abbreviated as ohm inverse like this. So now just observe, conductance is 1 by R we learn. We know the unit for resistance is ohm. That is 1 by ohm. So therefore, the unit for conductance will be what? Per ohm, or reciprocal of ohm, it says. So per ohm. Per ohm is the unit for conductance. According to SI system, the unit of electrical conductance is Siemens. So Siemens is represented as S. 1 Siemens is equal to 1 ohm inverse. So ohm inverse is otherwise called as what? Siemens. SIE-MENS. Siemens. Did you follow what is conductance? Simple conductance is the reciprocal of resistance. The unit for conductance is per ohm, or it is also called as Siemens. Remember that. Did you follow?
yes, sir.
The next. The inverse of resistivity is called as conductivity. There's a difference. Reciprocal of resistance is called as conductance. The reciprocal or inverse of resistivity is called as conductivity or specific conductance. It is represented by a symbol kappa, K-A-P-P-A. It's not K, it is a kappa, Greek letter, and it looks like K. The IUPAC has recommended the use of the term conductivity over specific conductance. It may be defined as conductance of solution of 1 centimeter length and having 1 square centimeter as the area of cross section. In other words, conductivity is the conductance of 1 centimeter cube of a solution of an electrolyte. Now, for an example, if I take the specific conductance we are talking about, now if I have two electrodes like this, the distance between the electrodes should be 1 centimeter and the area of cross section should be what? 1 centimeter square. So that means conductivity of the ions present here in this region only is called as specific conductance. We are not worried about the conductivity present outside this area. So in case of specific conductance, the distance between the electrodes is specific and area of cross section is also specific. Therefore, it is called as what? Specific. So it is defined as conductivity. It is defined as the conductance of a solution of 1 centimeter length and having 1 centimeter square or square centimeter as the area of cross section. In other words, conductivity is the conductance of 1 centimeter cube of a solution of an electrolyte. So kappa is the specific conductance is equal to 1 by rho. Rho is nothing but specific conductivity. So therefore, the unit for a specific conductivity is ohm inverse centimeter inverse or Siemens per centimeter inverse. Siemens per centimeter or Siemens centimeter inverse. Either ways, you can read it out. So remember, what is specific conductance? Conductance of all the ions present in the solution, in which the distance between the electrode is 1 centimeter and area of cross section is 1 centimeter square. That is called a specific conductance. And the unit for specific conductance is O per ohm per centimeter, or it's called as Siemens per centimeter, or it's called as Siemens per centimeter. In SI units, L is expressed in terms of meter and area of cross section is represented in terms of meter square. So the units of conductivity is Siemens per meter. Siemens per meter. Did you follow what is specific conductance? In case of specific conductance, the distance between the electrode should be 1 centimeter and the area of cross section is 1 centimeter square. Area is 1 centimeter square and the distance is 1 centimeter. So conductivity of all the ions kappa. Kappa is 1 by rho. Therefore, the unit for specific inverse, or we can write it as Siemens meters per meter in SI units. Molar conductivity or molar conductance. The next molar conductivity is defined as the conducting power of all the ions produced by dissolving 1 mole of an electrolyte in a solution. It is represented by capital lambda. Lambda. This is lambda. Molar conductance is related to specific conductance as. Now just remember, molar conductivity is defined as, or molar conductance is defined as conductance of 1 molar solution. In simple words, we can say conductance of 1 molar solution is called as molar conductance. And molar conductance is represented by the letter lambda. And the relation between molar conductance and specific conductance is this. This is important. Lambda is equal to K by M. What is this K? K is called as specific conductance. M is called as what? Molarity, concentration. That's called as molar concentration. If M is in the units of molarity, that is moles per liter, then lambda is expressed as lambda is equal to specific conductance into 1000 divided by M. K into 1000 divided by M. That's the relationship between specific conductance and lambda. Followed this formula, you should remember to work out some problems in the competitive exam. Can you remember? Molar conductance and specific conductance. What's the relation? Lambda is equal to K into 1000 by M. Into kappa into 1000 by M. Kappa is called a specific conductance. M is called as the concentration. See, sometimes they can represent this equation like this also. Lambda is equal to kappa into 1000 by C. C is nothing but concentration, molar concentration. Following?
Yes, sir.
Yes. For a solution containing 1 gram mole of an electrolyte, placed between 2 parallel electrodes of 1 square centimeter area of cross section and 1 centimeter apart. Same thing we learned. This is called as what's molar conductance. I simply told conductivity of 1 molar solution as what molar conductance. 1 gram mole of electrolyte means 1 molar. So conductance G is equal to conductivity, that is equal to molar conductivity lambda. But if the solution contains 1 gram mole of an electrolyte, therefore the measured conductance will be equal to molar conductance. Thus, molar conductivity lambda is equal to 100 into conductivity. In other words, lambda is equal to kappa, specific conductance into volume. See this kappa, we can define molar conductance as a product of specific conductance and volume. This also can be written as lambda is equal to kappa into 1 by C. Volume is inversely proportional to concentration. So lambda is equal to specific conductance into 1 by C. Or we can define molar conductance as the product of specific conductance and volume. Our lambda is equal to kappa into 1 by C, where V is the volume of the solution in centimeter cube containing 1 gram mole of an electrolyte. See, containing 1 gram mole of an electrolyte. Therefore, we can write V as 1 by C. We know that volume is inversely proportional to concentration. If M is the concentration of the solution per mole in mole per liter, then M mole of an electrolyte is present in 1000 centimeter cube. M moles of electrolyte is present in 1000 centimeter. So 1 mole of electrolyte is present in 1 into 1000 divided by M, 1000 by M centimeter cube of the solution. Thus, we write lambda is equal to kappa into volume, specific conductance into volume in centimeter cube containing 1 mole of an electrolyte. So the unit for molar conductance, they can ask you for 1 mark. It is Siemens centimeter square per mole. Siemens centimeter square per mole. Can you remember this? Followed?
Yes, sir.
Others?
Yes, sir.
And next is equivalent conductivity. It is defined as conducting power of all the ions produced by dissolving 1 gram equivalent weight of an electrolyte in a solution. So when you have 1 gram equivalent weight of an electrolyte in the solution, then 1 gram equivalent weight of electrolyte in 1 liter is called as 1 normal solution. So 1 mole in 1 liter is 1 molar. 1 gram equivalent weight in 1 liter is called as 1 normal solution. So conductivity of 1 normal solution is called as equivalent conductivity. This equivalent conductivity is represented as lambda E. This E stands for equivalence, lambda E. So equivalent conductance is related to specific conductance as a formula. Lambda E is equal to specific conductance by normality. Here we learned specific conductance into molarity, divided by molarity. Here it is specific conductance divided by normality. When we take equivalent weight, it is normality. Where N is the concentration, if N is the number of units of normality, I mentioned normality, that is gram equivalents per liter, lambda E may be expressed as. See, lambda is E is equal to kappa, specific conductance into 1000 divided by N, in terms of normality. In terms of molarity, the formula looks same, divided by the molar concentration, M. So same relationship, okay, all this is same. And the unit for equivalent conductance, you see, per ohm, centimeter square, gram equivalence. Or you can write Siemens centimeter square per gram equivalence. This is the unit for equivalent conductivity, Siemens centimeter square per gram equivalence, or per ohm centimeter square per gram equivalence. Factors affecting the electrolytic conductance. Factors affecting the electrolytic conductance. The first one is nature of the electrolyte. You tell me what will be the nature of the electrolyte. Strong electrolytes will have more conductance. Weak electrolytes will have less conductance. Because strong electrolytes will undergo complete dissociation, weak electrolytes will undergo partial dissociation. So conductivity depends on the nature of the electrolyte. See here, see, where's that? Strong electrolytes dissociates almost completely into ions, and therefore their solution have high conductance. On the other hand, weak electrolytes dissociate only to a small extent and give lesser number of ions. Therefore, weak electrolytes have low conductance. Did you understand what I'm telling? Strong electrolytes, more conductance because more ions. Weak electrolyte, less ions, therefore less conductance. Now, if I take 1 molar HCl and if I take 1 molar acetic acid and measure conductance, which will give more conductance? Which will give more conductance? HCl, acetic acid.
Sir, HCl.
Why? Because HCl is what electrolyte?
Strong electrolyte.
Strong electrolyte. Acetic acid is what electrolyte? Weak electrolyte. Therefore, as HCl will give you more conductance compared to acetic acid. So strong electrolyte. This is a strong electrolyte. And this is a weak electrolyte. Acetic acid is a weak electrolyte. The next one is concentration of the solution. You pay attention with this. Molar conductance of electrolytic solution varies with concentration of the electrolyte. In general, molar conductance of an electrolyte increases with decrease in concentration or increase in dilution. Just see the controversy here. Molar conductance of an electrolyte increases with decrease in concentration or increase in dilution. Why is this? You tell me. Molar conductance increases with decrease in concentration. I can say molar conductance is inverse. Why? When concentration is more, the ions are very close to each other. When ions are close to each other, they can form an ionic compound. There won't be free ions for their mobility. That is why they say molar conductance decreases with increase. Molar conductance increases with a decrease in what? Concentration. Or when you decrease the, what do you mean by that? If you dilute it, the concentration decreases. That is why they say on dilution, what happens? Conductance increases. On dilution, concentration decreases. Therefore, what happens? Conductance increases. Did you follow this? Generally, we talk molar conductance or any conductance increases with increase in concentration because we have a general idea that ions will be more in number, therefore conductivity will be more. But here they say clearly, that's a general trend, true. But highly concentrated solution we cannot take. When we take highly concentrated solution, the ions will come close to each other. The ions will be very close to each other. Therefore, it can form an ionic compound. Instead of free ions, you will have an ionic solid. Therefore, conductivity will decrease on increase in concentration. That's what they say. This is an important point for you to understand. Molar conductance of an electrolyte increases with decrease in concentration, or molar conductance of an electrolyte increases with dilution. Did you follow this? We will learn the statement. The molar conductance of strong electrolyte, HCl, KCl, KNO3, as well as weak electrolyte like acetic acid, ammonium hydroxide, increase with the decrease in concentration or increase in dilution. The variation, however, is different for strong and weak electrolyte. So how much increase or how much decrease, that varies with strong electrolyte and weak electrolyte. The variation of molar conductance with concentration can be explained on the basis of conducting ability of ions for weak and strong electrolytes. Conducting ability of the ions for weak and strong electrolytes. Did you follow this? Molar conductance decreases with increase in concentration, or molar conductance increases with increase in dilution. I gave you the small information why it's so. Followed with this.
Yes, sir.
Yeah. Just to satisfy me, you are telling, or you truly followed?
No, sir. Truly followed, sir.
Liar. No?
No, sir. No, sir.
No. Okay. Now, for weak electrolytes, the variation of lambda. What is lambda? Lambda is molar conductance. The variation of lambda, molar conductance, with dilution can be explained on the basis of number of ions in the solution. The number of ions furnished by an electrolyte in solution depends upon the degree of dissociation with dilution. See here, the number of ions furnished by an electrolyte in solution depends upon the degree of dissociation with dilution. What is this degree of dissociation? We will learn. Now, before we understand the degree of dissociation, we should understand this weak electrolyte undergoes partial dissociation. So partial dissociation is represented like this. Acetic acid, we take an example. It will dissociate partially to form acetate ion and H+. Now this reversible arrow indicates at one stage there will exist an equilibrium. What is equilibrium here? The speed at which acetic acid dissociates to form acetate ion and H plus ion, the same speed this acetate ion and H plus ion will give backward acetic acid. So rate of forward reaction is equal to rate of what? Backward reaction. That stage is called as chemical equilibrium. Stage where rate of forward reaction becomes equal to rate of what? Backward reaction is called as what? Chemical equilibrium. Yes or no?
Yes, sir.
Yes, sir.
Now, this degree of dissociation is in this equilibrium or at this equilibrium, very small amount of the electrolyte it dissociates is dissociation. A fraction of electrolyte, a small amount of electrolyte, which it dissociates at equilibrium is called dissociation. This degree of dissociation is represented as alpha. Degree of dissociation is represented as alpha. Now, with the increase in dilution, the degree of dissociation increases. As a result, molar conductance increases. Now assume it is not true. Assume. Now I've taken 1 liter of water. I've taken 1 liter of water and I've added 10 molecules of acetic acid. 10 molecules of acetic acid I've added. This 10 molecules of acetic acid, only 2 molecules of acetic acid will dissociate to form 2 acetate ion and 2 H plus ion. Now tell me in the solution, how many ions are there now? How many ions are there? How many ions are there? I told I'm taking 10 molecules of acetic acid. From 10 molecules of acetic acid, 2 molecules are dissociating to form 2 acetate ion and 2 H plus ion. So how many ions are there here?
So 4.
4 ions are there. Very good. 4 ions are there. There are 4 ions. Now, I add 1 more liter of water. That means I'm diluting the solution. When I add 1 more liter of water, now what happened? 8 was there here. From this 8, 2 more dissociates. So you'll get 2 plus 2. Totally, how many ions will become now? Plus 4. Totally, it becomes how many ions?
8 ions.
So Nodi, what happens is when you dilute, the dissociation of the weak electrolyte increases. So dissociation of weak electrolyte, when it increases, the number of ions formed will be increasing. So when the number of ions formed is increasing, conductance also increases. That's what the statement. With the increase in dilution, the degree of dissociation increases. See, at 1 liter, only 4 ions were there. When dilute, furthermore, degree of dissociation, ionization or dissociation increases. Therefore, what happened? Number of ions formed is more. Therefore, conductance also increases. Did you understand? This is for what electrolyte we spoke about? Weak electrolyte.
So weak electrolyte, sir.
Yeah. Now, the limiting value of molar conductance, the lambda naught is called as limiting value of molar conductance. It corresponds to degree of dissociation equal to 1. That is, whole of the electrolyte dissociate. Now, just observe. Now, 2 liters when I add water, you told 8 minus 2. How much is left out? 6 is left out. If I add 1 more liter, from 6, 2 more dissociates. Add another 1 more liter. From you'll be having 4, another 2 dissociates. Add 1 more liter of solvent. What happens? All the electrolyte will dissociate or not? Yes or no?
Yes, sir.
So that means any weak electrolyte at infinite dilution will behave like what? A strong electrolyte. That means at infinite dilution, all the ions of the weak electrolyte also will dissociate. That is called as limiting value of molar conductance, represented as lambda naught. What is lambda naught? Lambda naught is the conductance at what? Infinite dilution. Infinite dilution is what we expect. All the weak electrolytes would have dissociated. So ions formed will be what? More. Therefore, conductance will be more. That's called as lambda naught. That's otherwise called as limiting value of molar conductance. Lambda naught. Now, thus, the degree of dissociation can be calculated at any concentration. Alpha, degree of dissociation is alpha. Alpha is calculated as lambda C by lambda naught. What is lambda C? Lambda C is molar conductance at a particular concentration. Lambda C, maybe I can say lambda C is equal to conductance at 0.1 molar concentration. Lambda naught is conductance at what dilution? Infinite dilution. At infinite dilution, we expect the electrolyte to be completely dissociated. So this is the formula to calculate degree of dissociation. Alpha is equal to lambda C by lambda naught. What is lambda C? Conductance of the electrolyte, molar conductance of the electrolyte at a particular concentration. That's called as molar, lambda C. What is lambda naught? Lambda naught is molar conductance at infinite dilution. That's called as lambda naught. Did you follow this?
Yes, sir.
That's with respect to what? Weak electrolyte. Now, weak electrolyte, what happens? As you dilute, dissociation increases, conductance increases. So degree of dissociation is equal to lambda C by lambda naught. But in case of strong electrolyte, already the dissociation is full. HCl, if you take, this HCl will undergo complete dissociation to form H plus and what? Cl minus. Why it's not writing? Cl minus. So if I take 10 HCl molecule, you will get 10 H plus and 10 Cl minus. Already the dissociation is complete. Now, then what? There is no increase in number of ions when you dilute, because strong electrolytes are completely ionized in solution at all concentration. So strong electrolytes will undergo complete dissociation even at minimum dilution. However, in concentrated solution, electrolytes, concentrated solution of strong electrolyte, there is a strong force of attraction between the ions of opposite charge, called as interionic forces. Due to these interionic forces, conducting ability of the ion is less in concentrated solution. We learned as the concentration increases, molar conductance decreases, I told you, because of the increase in what? Interionic force. When the concentration increases, ions are close to each other. Therefore, interionic force increases. Therefore, conducting ability of this ions decreases. With dilution, ions become far apart from one another. So interionic force decreases. So even for a strong electrolyte on dilution, conductance will increase because interionic force will decrease. As a result, molar conductance increases with dilution. When the concentration of solution becomes very low, interionic attraction becomes negligible and molar conductance approaches the limiting value, called as molar conductance at infinite dilution. Thus, this value is characteristic of each electrolyte. So that means molar conduction, lambda naught, this is molar conductance at infinite dilution. Lambda naught is a characteristic of electrolyte. It varies from electrolyte to electrolyte. It's not common to all. It is not a constant for different electrolytes. Okay, so it's not constant for all the electrolytes. So it varies from electrolyte to electrolyte. That's the first one, nature of electrolyte. The second one is concentration, we learned. Third one, how conductivity is depending on temperature. Conductivity of an electrolyte depends upon the temperature. With increase in temperature, what happens? Conductivity also increases. Why? As we increase the temperature, what happens? Kinetic energy
of ions will increase.
Therefore, what happens? Conductivity will increase. So this is what the factors affecting conductance. What are the factors affecting conductance? One is nature of the electrolyte. The second one is concentration. And the third is what? Temperature. These are the three factors which affects the conductance. Now, a few questions we will learn. Shortage of time. We'll learn a few questions and then we will continue with the problems based on conductance in next class. Now, a few questions. The first question, the specific conductivity of n by 10 KCl. What do you mean by n by 10 KCl? Can I write it as 1 by 10 n KCl? Can I write it as 0.1 normal KCl? All right. N by 10 means what? 0.1 normal KCl. Because n by 10 can be written as what? 1 by 10. 1 by 10 is what? 0.1. So 0.1 normal KCl. They've given specific conductance of n by 10 KCl at 20 degrees Celsius is 0.0212 per ohm centimeter. That means they've given kappa. Kappa they've given us 0.0212 units they've given. And the resistance of the cell containing the solution at 20 degrees Celsius, resistance they have given it as 55 ohms. They're asking you to calculate cell constant. They're asking you to calculate cell constant. Now you should remember, specific conductance is directly proportional to length and inversely proportional to area. We learned it. Conductance is directly proportional to length and inversely proportional to area. Remove the proportionality sign, you give a constant. K is equal to C into L by A. Or we can write this as L by A is equal to K into 1 by C. Now 1 by C, inverse of conductance is called as resistance. That is specific conductance into R. C is not concentration here. It's a constant. So this is called as conductance here. So inverse of conductance is called as resistance. So specific conductance, we know it is 0.0212. Resistance is 55 ohms. On simplification, we will get 1.166 centimeter inverse. So therefore, the answer for this question is option B. Can you remember this formula? Cell constant is L by A. Cell constant is length by area. In terms of electrochemistry, cell constant is L by A. Possible to remember?
Yes, sir.
Yes, sir.
Question, yes. The next question. Electrical conductance through metals is called as metallic or electronic conductance and is due to the movement of electrons. The electronic conductance depends on nature and structure of the metal, number of valence electron per atom, change in temperature, all of these.
So all of these, sir.
It is all of these. It depends on the nature and structure of the metal. It depends on the number of electrons present in the outermost shell. It also depends on the temperature. Now, for metallic conductor, remember, as temperature increases, resistance also increases. Conductivity will decrease. The next question. What would be the equivalent conductivity of a cell in which 0.5 normal salt solution of a resistance of 40 ohms, whose electrodes are 2 centimeters apart and 5 centimeters in area? So we know that K is equal to 1 by R. Conductance is equal to 1 by R. That is into area, length by area. Or what is this? Specific conductance is proportional to, or conductance is proportional to length and inversely proportional to area. If you remove the proportionality sign, we give proportionality constant. That constant is given as C. C into L by A. What is C? C is conductance. So conductance is nothing but inverse of resistance. That's why we have given 1 by R here. So this specific conductance will be equal to 1 by 40 because the resistance they have given us 40 into length they have given us 2 centimeter and area they have given us 5. So 1 by 40 into 2 divided by 5. What is the question they're asking? What would be the equivalent conductance? In order to calculate the equivalent conductance, lambda equivalent conductance is kappa into 1000 divided by n. Kappa we found out here, that is equal to 1 by 40 into 2 by 5 into 1000 divided by, what's the normality they've given? 0.5 divided by 0.5. On simplification, you will get 20 ohm inverse centimeter square per equivalence. Therefore, the answer for this question is option B. Followed?
Yes, sir.
Yeah. If you followed, you tell me this problem, the fourth problem. Anybody can help me out doing it. Very simple problem. Molar conductance of 0.15 molar solution of KCl at 298 Kelvin. If its conductivity is 0.0152 Siemens centimeter inverse will be. What is the molar conductance? Tell me. What they've given, its conductivity Siemens centimeter, the specific conductance they've given. Kappa they've given us 1.5, not 1.5. What's that? 0.10152 Siemens centimeter inverse. This is kappa they've given. And they've given the concentration as 0.15 molar. Temperature we don't require. We know that molar conductance is equal to specific conductance into 1000 divided by concentration or M. So kappa is 0.0152 into 1000 divided by what's the concentration they've given? They've given us 0.15. On simplification, we will get it as 101 ohm inverse centimeters inverse per mole. So you can simplify this. Very, you can shift the decimals and cancel it out. So the answer you'll get is around 101 ohm inverse centimeter square per mole. The next question, followed with this.
Yes, sir.
Yes, sir.
Now tell me the answer. Then the fifth question, next question, you have to tell me the answer. All right. Molar conductance is maximum for the solution of concentration. Tell me the answer. Molar conductance is maximum for the solution of concentration. Tell me.
So option
Sir,
D.
0.005 M, sir.
Option?
So option C.
What's option? Option C.
So option C, sir.
Very good. Option C. Now you tell me what it is. Now you tell me.
Sir.
Now you tell me. Now
So
can I say
option D.
molar conductance is inversely proportional to concentration? No. This M is concentration, molarity, or we can write this formula as kappa into 1000 by C. Molar conductance is inversely proportional to what? Concentration. Lambda is inversely proportional to concentration. It's in the denominator. Which
Yes,
will be
sir.
the maximum? Which
Sir.
will show maximum? Huh?
0.001 molar.
Sir,
Option D, 0.001 mole. See, molar conductance is inversely proportional to concentration. As per this formula, this is molar conductance and this is concentration. How they are related? Inversely, no? That means if this to be maximum, this should be what? Minimum. So what's the answer for this question? It will be option D.
Option D, sir.
Yeah. Remember this. Remember this. The next problem. The specific conductance of saturated solution of silver chloride at 25 degrees Celsius is 1.821 into 10 to the power minus 5 mho. Mho is nothing but ohm inverse, centimeter inverse. What is the solubility of AgCl in water if the limiting molar conductance of AgCl is 130.26 mho centimeter square per mole? See here, this formula we never learned, but remember this. Solubility is given by the formula kappa into 1000 divided by lambda naught. What is this lambda naught? Limiting molar conductivity. Limiting molar conductivity is kappa. Specific conductance they have given as what? 1.821 into 10 to the power minus 5 into 1000 divided by lambda naught is 130.26. So that will be equal to 13.97 into 10 to the power minus 5 mole per liter. This is the solubility. What they're asking, what is the solubility of AgCl in water in gram per liter they're asking. Here it is in mole per liter. Since we want gram per liter, we have to multiply it by its molecular mass. So silver chloride, the molecular mass is 180 is atomic mass of silver, 35.5 is the atomic mass of chlorine. So it is 143.5. So that's therefore 13.97 into 10 to the power minus 5 into 143.5. That will be giving you 2.004 into 10 to the power minus 2 gram per liter. Therefore, the answer for this question is option C. All right, did you follow this?
Yes, sir.
Students followed?
Yes,
Yes,
sir.
sir.
All right, the rest of the questions will continue in the next class. All right, madam, I'll stop the class, ma'am. Ma'am, can I stop the class?
Yes, sir. Yes, sir. Thank you,
Yeah.
sir.